Welcome to Secure Software Development. We're going to begin, as we begin every class, by talking about Polkit, which is a package for privilege escalation. Not the bad kind necessarily, just privilege escalation generally. There are some times when you need to be the super user to do certain things, like install software or make changes to a configuration. And Polkit is the Linux utility on some Linuxes that lets you do that. It's a package for privilege escalation. The most common interaction with it is that you would take some action and a pop-up would occur saying, hey, I need you to authenticate. And you would put in your password and click authenticate, and it would then elevate you to super user and you'd be able to do what you wanted to do. You can do this from the prompt. You can run pkexec, that is the actual utility you would run. And in this case, I'm saying I want to run cat as root. So cat just types out the contents of a file. And I want to look at the shadow password file. That's the one that contains the hashes. So the executable pkexec is what we would call setuid. That is, when you run it, it sets the effective user ID to its own user ID. Now, what's going on here? Well, your actual user ID is just the ID of your user. The effective user ID is a separate thing, and that's the ID that allows you to take certain operations. So in this case, because setuid is owned by root and it is marked as being setuid, when you run it, it runs as if you were root. And so that means that it can do certain specialized things. You can see this by listing it. So if you do an ls-l on pkexec, you'll see this little S right here, which indicates in this little owner section that it is setuid to the owner, and you'll notice that the owner is set to root. There's a set group ID bit as well, and the group is set to root here. If you run file on it, say give me information about this file, it'll tell you explicitly that it's setuid. So, Qualsys found a vulnerability in this, and they named it Polkit. So here's what they said. They discovered a memory corruption vulnerability in pkexec, a setuid program that is installed by default on every major Linux distribution. This easily exploited vulnerability allows any unprivileged user to gain full root privileges on a vulnerable host by exploiting this vulnerability in the default configuration. There's a lot of things coming at you there, but basically this vulnerability allows you to become root and then do whatever you want to as root. It's a very, very serious vulnerability. So let's go over again what these different things are. A weakness in a system is just a point where security is weak, or maybe it's poorly designed, or maybe it's just poorly executed, or it's fragile. That is, it depends on some external circumstances, and they may or may not be true. Right? The security of your system depends on somebody going by and visually confirming that something has been done, and that can make it fragile because maybe they won't always do that. It can be poorly executed because maybe the security guard you hired has a second job, he's tired and he falls asleep. It can be poorly designed because the cameras you installed are not looking in a good direction. And it can be weak because maybe you picked a particularly bad type of alarm system that's easily bypassed. A vulnerability is a weakness. Actually, it can be multiple weaknesses together that make up a vulnerability. but it's weaknesses that can be exploited by a threat actor, an attacker, to cross privilege boundaries within a system. So I'm throwing lots of words at you here. A threat actor? Right, somebody, an actor out in the world who poses a threat to your system. You can just think of him as an attacker. Privilege boundaries? Well, for example, I should be able to add a user to my system, but you shouldn't be able to add a user to my system. It's mine. There's a privilege boundary there that separates the privileges that I, as the system owner, have, and that you, as not the system owner, shouldn't have. An exploit is a specific collection of techniques or tools that, when combined with one or more vulnerabilities, allow a threat actor to cross a privilege boundary within a system. The exploit is actually the mechanics of doing whatever the attacker wants to do. It's whatever they need to do to accomplish their mission. Now, I didn't mention computers anywhere in this. A thing being attacked could be a car, a building, a museum, a casino, a computer program, a spacecraft, whatever. Okay? But that's the basic idea. A weakness can exist, but if you don't know how to use it to cross a privilege boundary, then it's not a vulnerability. Maybe you'll figure that out in the future. A vulnerability implies that there is both at least one weakness and an exploit, right? A system isn't vulnerable until an exploit is discovered. You can have lots of weaknesses, but if no one knows how to use those to exploit your system, then it's not vulnerable. Hope that makes sense, right? It's vulnerable to exploit when there is an exploit. Multiple weaknesses of different components can be combined, right? You don't have to have just weakness equal vulnerability equal exploit. That's not how it works. There can be a weakness, but it's maybe you can't really get anywhere with that. There could be a second one and a third one, but maybe when you combine all three weaknesses, now you've got an exploit. And we're going to see an example of that. Now, we already know there's a vulnerability in pkexec. So it's reasonable to ask, what was the weakness? They said something like memory corruption? Let's go take a look at what it is. And I'll remind you of this important point. Vulnerabilities commonly arise when one system or component interacts with another. So they occur at these interfaces. So we'll look for that. They occur when the entire input space hasn't been properly considered. So we should look for that. And they occur where there's a convention that is assumed but not enforced. I've mentioned all these points before, but bear these three things in mind, okay, as we look for the vulnerability. So here is the vulnerable code from pkexec. This is an excerpt from pkexec.c taken out of the GitHub page where it is stored. Insecurity can be in a system for a long time. This one happens to have been there since the beginning, since this was first introduced into Linux in 2009. So it's been around a long time. And the vulnerability is visible on the screen right now. So I would encourage you to pause here and take a look. You see I've commented out some code, but that's okay. Pause here, take a look, see if you can figure out what the vulnerability is. If you can't, that's okay. If you can, that's great. But take a look and give it a try. When you're ready, resume. Okay, I assume you're ready to go on. The vulnerability, I'm saying the wrong word. The weakness here is argc potentially being 0. Now wait a minute, you may say to me, argc can't be 0 because you always have to have the name of the program as the first argument, right? argv0 is going to be the name of the program. So there's at least one thing in the argument list, so argc has to be at least 1. Well, okay. I'll buy that. That sounds right. But then I have to ask, what enforces that? How does the program name get put in argv? Does the kernel do it? How does that happen? It turns out the caller has to do it. Okay? So if you've ever written code that does a fork and exec, then you'll know about this. So here we see some code, and that code calls exec_v. And exec_v is a form of the exec system call that takes the name of a program and it takes the argument list. And if you look at that for a few seconds, you'll see that argv is effectively empty. It just contains the terminating null pointer. Remember, the argument list is a null terminated list of strings. In this case, that list of strings is just null. So that means the argument list is empty. If the argument list is empty, argc is going to be 0. So it's entirely possible to have argc be 0. In fact, it's easy. There's the code that does it. Oh. Okay. Well, it turns out this is going to be a problem. We'll see why in a few minutes. It's been fixed on Linux. And fixed, sure. The way it was fixed is a change was introduced into the kernel so that if a process tries to start another process with an empty argument list like we just saw, the following things happen. An empty string is added to the arguments. argc is set to 1, and you get a kernel message telling you that this happened. So it's going to make a change to your argument list, but only when it's empty, which is a weird condition that should never really happen. Over on the left-hand side, there's a little program that you can run, and what it does is it tells you about the arguments. If you look at it, you'll see it prints out argc, then it prints out each of the argv entries, and it prints them out as array equal, and it gives you the address of the string and then the string itself. So it writes out a lot of information. Then it writes out envp, which is the next thing. It's the environment pointers. It writes all of them out in the same way. So it'll show you all the stuff that's an argument to the program. And if you want to try it, try running it with an empty argument list and see what you get. The code to do that is over on the right. So do that. There's the line down below to build both of them, and then you could just run it and see what you get. They have to be in the same directory, obviously, because this one is going to try to run it as args, and so it needs to find args in the current folder. So what? So argc is 0. Big deal. Do I care? I don't care. So let's see. What does that even mean? Well, let's take a look. The first thing that will happen, the first thing we care about happening, is we come into this for loop. And so we set n equal to 1, and while n is less than argc, that gu int is a GNU standard C library thing. Don't worry about it. Just treat it as an int. Cast. While n is less than argc, then we increment n. Okay, well, n is in fact not less than argc because argc is 0 and n is 1, so this loop will never run. Alright, fine. So the loop doesn't run, and we drop down here. Okay. Does that matter? Well, that's an assertion. So we check to see if argv of argc is equal to null. Well, what's argc? It's 0. What's argv of 0 when we call it with no arguments? It's null. So that assertion is going to pass, right? Nothing wrong there. It is in fact the case that argc is null. All right, fine. Okay. So what happens next? Well, let's go and look at the stack. So this is the stack for our little process, the little piece of code that we're running. This is what it would normally look like for any arbitrary process. So up here is the top of memory. The stack grows downward, and it's not by top of memory. I don't really mean top of memory. I really mean it's the top of the stack space. The stack grows down as stuff is pushed onto it, and the stack pointer points at the most recent thing that has been pushed onto the stack. Okay, so what's at the top of the stack, or at the bottom of the screen on the right hand side? argc. There's argc. Right above it is the first argument, argv0. The arguments continue until you get to the last one, which would be argv, argc-1, and then the terminating null. And then you have the environment strings terminated with a null. Those are the environment strings, like your home area, the current path environment, basically all the environment variables that have been passed to your program when it started. And you can control that too. Exec VE will let you set those. And that's followed by auxiliary vectors. Auxiliary vectors. Well, these are things that are filled in to pass information from the kernel to your process. And there are several of them. And they're terminated with the special double keyword null. So 2 nulls in a row. Beyond that is other stuff. If you're wondering where the actual content of the environment variable strings are stored, they're stored up here. So there's a whole bunch of stuff that's stored up here. This is what the stack looks like for any old process. But our process isn't any old process, right? argc is 0, which means it really looks like this, right? So we have the argument count, and then we have the terminating null because there's no arguments, and then we have the environment. Wow, so in this case we have argc equals 0, argv0 is null, so what's argv1? Well, this is argv0, and based on pointer math, argv1 is pointing right here. So argv1 is actually the first environment string, envp0. First thing that's passed in from the environment. Okay, so be sure you got all this in your head right now. We're able to invoke a program with no arguments, which means that argc is 0, which means that argv contains only the null, but because of pointer math, argv1 actually points to the first string of the environment. So what's envp0? It's just an environment string. Now, if you start a process, you can control what environment variables get passed. You'll do that with execve. Now, pkexec is a setuid program, and because of that, it will have its environment variable list cleaned of any exploitable variables by the dynamic linker. Now, I don't want to get into too much technical detail, but when you start a program under Linux, you use a program loader, in this case the dynamic linker. It's responsible for doing various things, starting your process running, loading in the dynamic link libraries, resolving all that stuff. It does quite a few things, including relocating your program to a random memory location if address space layout randomization is on. You don't care about any of that. What you do care about is the dynamic linker is there to do some things to protect you. And one of the things it does to protect you is it removes exploitable environment variables from the environment. What's an exploitable environment variable? We're going down a deep rabbit hole here. So, environment variables control a lot of the way the system works. One of them, for example, is LD preload. So the LD part means that it refers to the linker. Okay? And preload is just what it does. In this case, if I put stuff in LD preload, then the linker will load that into memory first. So what I could do is I could set the environment variable LD preload to point to a library that I had built, which contains some malicious code. Then, when this thing runs, because LD preload is set, and it's running as root, it will load my malicious code in. And I could name my malicious functions things like malloc or printf. And so when it tries to call malloc or printf, before it gets to the standard library one, it gets to mine first because it was preloaded. So it's the first thing in the search path. And it runs my malicious malloc or my malicious printf. So that's bad. So what happens is the loader cleans that up. It gets rid of LD preload, so I can't use that exploit. Ah, darn it. I guess the game is over. Alright, so let's keep going looking at the program. We know what happens. We start it with no environment variables. The loop doesn't run. It just sets into 1. That's all it does. The assertion passes. Then we come down here and we do this piece right here. Path equal G string dupe argv_in. What's argv_in? Well, it's argv1. And remember that argv1 is just envp 0. It's the first environment variable. So what happens is this, whatever's in that first environment variable, gets put into path. Now we check to see if path is null, and it's not going to be null. So we won't do this. We'll come down here and we'll see if path 0 is a slash. Okay? If it's not a slash, we want to then go and find the program in the path. So if the first thing is a slash, we assume it's an absolute path to a file. But if it's not, we assume it must be something that's in our search path, in the path environment variable. And we need to go find it. So we'll go find it and do some stuff. Okay? And if we find it, then we free up path, and then we also set argv_in, that's argv1, to whatever we resolved it to be. Okay. What's just happened, right, is if argc had not been 0, then I would have looked for help, and if I didn't find it, fine. I would have then checked to see that I was at the end. I would have gotten the correct entry. It was not null. I would have looked for it. I would have found it, and I would have set argv_in to be the resolved path. So, in other words, this first thing would have been the thing I want to run as root. If it had an absolute path, fine. If it didn't, I'd search for it in the path and then modify the argument list so that it had the correct full path to it. That's not what happened, though. I didn't pass any arguments. So instead of doing anything here, I just set n equal 1. And then down here, I set argv1 equal to whatever path I found based on looking up the environment variable contents. And then I set the environment variable to whatever I found. So I have just set an environment variable. Now, that could be a bad thing depending upon what that environment variable is. I might be able to push back in an exploitable environment variable using this trick. Okay, if you keep reading in the pkexec code, you'll see this. Now save the environment variables we care about. So you make a new array, we walk through the ones we want to save, and then there's this great comment. To qualify for the paranoia gold star, we validate the value of each environment variable passed through. This is only to attempt to avoid exploits in potentially broken programs launched via pkexec. So the comment basically says, I've done everything right, But other idiots out there might have some problems in their program, but I'll fix it here. That comment did not age well. Because, as it turns out, there can be something in here we can exploit. Now, if there's an error message generated, so for the moment, set everything else aside, if an error message is generated, pkexec needs to print it out, and it uses gPrintError to do that. The GNU library's print error message. We can cause an error to be printed after the path is created. So, search for a convenient gPrintError after the path is assigned to argv1, which is actually envp0. But that's just going to print a string, right? So it should be fine. Well, bear with me here. There's a lot going on, and there are a lot of moving parts, but bear with me. What if the char set is not the UTF-8 char set? Well, we can set char set wherever we want. It's not a exploitable environment variable. Therefore, we can set it and it's preserved. So if I set char set and then I invoke Polkit with no arguments, the char set gets passed into it and I can set some other encoding. But that doesn't seem like a problem, does it? Well, gPrintError will then call the glibc function iconvopen to convert from UTF-8 to the correct character set specified by the char set environment variable. So it's going to then call this routine to do that conversion. Okay, so if you keep reading the environment page for that, it turns out that to convert, it uses small shared libraries, one for whatever conversion it has to do. It loads those at runtime, and it uses gconv_path to find the library to load that contains the code it should run to do the conversion. What about gconv_path? That specifies the location of code to run. If I can manipulate it, then I can point it to my malicious code. And so what will happen is it'll go get something to convert UTF-8 over. I will have set gconv_path using that zero argument trick we saw earlier. Lets me set an environment variable. So I'll use that somehow to set an environment variable. I'll point gconv_path to my malicious code. Forcing it to print an error message causes it to call the converter. The converter then looks at gconv_path and loads my malicious code and runs it. And now I've got my malicious code running as root. Problem solved, right? Well, no, not really. This is a known problem. When you run a setuid program, the dynamic linker cleans up the environment, and gconv_path is known to be exploitable, so it's one of the ones the dynamic linker removes, just like LD preload. But wait, didn't I say I could use that trick, the zero argument trick, to modify the environment? Yes, I can do that. All right, this is all beginning to come together now. So let's create a folder and have the folder name be gconv_path equal period. I mean, that's literally going to be the folder name. Okay? And if you look at that, that's an environment setting. That's our folder name. And we'll add a file to that folder, and we'll just, I don't know, we can just call it friend. Now, we specify a char set. Then we invoke pkexec with argc0, and the path is constructed with envp0 equal friend, and a search path that matches gconv_path equal dot, and that results in us finding it and updating the environment as you see there. gconv_path equal ./friend. That seems like a lot to go through, and you should probably stop at this point to be sure you understand what the heck is happening, because a lot of stuff's happening. But that will set the path to point there. Okay, now over on the right hand side we have some exploit code, and that's the code that does the thing we just talked about. So let's walk through it real quick. Here's my main function. I create an argv that contains null because I want argc to be 0. I create an environment list, which the 0th entry is just friend, and then the first entry is path equal gconv underscore path equal period. So what I'm doing is I'm assigning gconv underscore path equal period to the path environment variable. And remember, when we search for whatever we're searching for in the path, we'll search here. So this will look for friend in this path. It'll find it because we put the friend file in that folder. It will then construct this as the final result and write it back to the 0th entry. So gconv path equal ./friend will overwrite friend that was here, and that'll be the new environment entry. Alright, so now gconv path is now, the exploitable environment variable, is now back in our environment. And what's our char set? Well, it's Wordle. What is the Wordle char set? It's one I made up. Okay, and there's a null terminator for the environment list. Then I use exec_ve, right? Exec_ve is the one that takes the environment. I give it the thing to exec, in this case pkexec. I give it the argument list, I give it the environment list, and then I'm done. Whew, this is a lot going on here. What was that Wordle thing? Well, here it is. If you look over on the right hand side, you'll see my Wordle character converter, which I will have to then compile to a library that can be found. Here's my init, doesn't do anything. Here's my end, doesn't do anything. Here's my convert. I could have put this code in any one of these. It would have been fine, but I put it in convert just because. I ignore all the stuff it's giving me, and all I do is set argv to be user bin bash. I set my environment. I give it a basic shell, a basic path that contains local sbin, local bin, sbin, bin, sbin, bin. That's it, the usual default path. And then I say set my user ID to 0, set my group ID to 0. Those are the values for root. I'm allowed to do that because I'm a setuid program. And then I do an exec. So what this will do is this, if I can get this code to run inside, pkexec runs this code, it will start a bash shell as root. And that's what I really want. Now, so I compile this, I add it to the list of gconv modules, I shove it in a local directory, and I run it, and I'm root. It'd be great if someone had known that this could happen. By the way, I've left out one little detail of this, which is how to cause the error message to happen. If you really care about it, I'm happy to share my exploit code. This is all code I developed. I actually developed an exploit for this when it first came out. I used to give talks on this. That's why this is so ridiculously detailed. It'd be great if we knew about this in advance. Well, it turns out that way back in December of 2013, somebody complained about this, and they said, most programmers should be aware that the argv argument to main is a null terminated list of strings. On Linux, argv can be specified as null, and this could cause a problem. This allows us to execute an application with argv 0 is null. I haven't found any potential exploits using this, but it does allow for some amusing behavior from setuid binaries. He didn't know about it because the Polkit hadn't been introduced yet, but it would be, and then it would be in there for a long time. So let's talk about unexploitable vulnerabilities. Recall the log4j vulnerability. Suppose we write our code such that it checks for a protocol prefix in a string being passed to the logger and removes it. So if we have something of that form, $ open curly bracket, some stuff, close curly bracket, we just delete that. Well, the weakness is still present in the log4j library, but for uses from our code, it cannot be exploited. Now, there could be other libraries that use log4j, and it may still be exploitable through them, but our code is trying its best to protect it. Now, it could be argued that the vulnerability is gone because we've explicitly closed the loophole, but I think that can be misleading. An adversary could find a way around our protective measures, and as an example of that, we just did that using Polkit. Right? We found a way around the protective measures, protecting you against malicious environment variables in order to set one and become root. So, we could call this an unexploitable vulnerability, which is to emphasize that, yeah, we know the vulnerability is still there, but we've taken steps to protect the system against it. Okay? This is not that uncommon to practice. Often, people have software installed and running, and yes, they know it's vulnerable. And because of regulations, especially in the energy sector, they have to account for that vulnerability. And so they make an argument that it's unexploitable. The vulnerability is still there, but it's unexploitable because of certain other measures they've taken around it. This is a common practice, something you should be aware of. It's a weird term. Unexploitable vulnerability seems like an oxymoron, but there you go. So, after all of that, what are the implications for software development? You should be aware of assumed but unenforced standards, like the first argument is always the program name. And you should be aware of seemingly unexploitable vulnerabilities. A lot of work was done to protect against malicious environment variables, but they could still creep in. Okay? That's what we did. All right. Define the structure of information and write code to validate the structure. That's it, right? Define the structure of information and then do checking. If another system does not expect a null pointer from you, or an empty array, or some other degenerate case, don't send them one, but instead generate an internal error. And if you don't expect to get one, check for it and generate an error, right? If you don't expect the argument list to be empty, make sure it's not empty. All right. Let's talk about physical protection. So, over on the right, we see the 5 basic functions of implementing physical protection. Sometimes you'll hear 3 Ds and 3 Rs, fine, but most of the time you'll find these 5. The focus is on defending an area, an item, a person, something, and you want to use multiple approaches. And you can organize your defense of that in terms of detection, deterrence, delay, response, and neutralization. And we'll go through what all those are next. So deterrence exists to prevent somebody from even trying to attack you. Right? Come at me, bro. Okay? You provide a credible threat of some unacceptable counteraction, right? If you come at me, we're going to sue you, or we're going to put you in jail, or we're going to shoot you. Okay, you try to make the result of an attack serious enough that it outweighs the perceived benefits. Okay, and so no one tries it. Okay. You can do this in a number of ways. You can do it with laws. You can do it with credible threats. Just a whole bunch of different things that you can do. There are laws in the U.S., for example, against computer trespass, but those only apply within the reach of the U.S. So what we've done since then is have State Department sanctions. So you're in a foreign country and you feel like you're immune, so you attack, but the State Department can issue sanctions, and we can seize money, we can prevent you from traveling, and do other stuff like this. If you want to look up the Palermo and Budapest Conventions, there's a link to them there, and that'll give you some sense of what's being done to try to deter international hacking. Detect. Detect is pretty obvious, right? We want to detect you, so we set up cameras, or we bury fiber optic cables to detect people walking, or we do other sorts of things to try to detect someone coming in. Detection is the positive assessment that a specific object caused an alarm, or the announcement of a potential malevolent act through alarms. Now, the problem with detection with alarms is, what if you get too many? Well, if you get a lot of false positives, right? If the buried fiber optic cable at the perimeter is always being set off by deer or wild turkeys or other things in the woods, you're going to quit paying attention to it. So this is called alert fatigue, and we want to avoid that. So you have to tune systems carefully so that you're not constantly having false alarms that you would then ignore. As an aside, I mentioned false positives. Let's think about what that means. You probably are hopefully familiar with the idea of a confusion matrix, but just in case you're not, this is an example of a confusion matrix. It's a tool used to visualize how a predictor performs. So for example, the actual condition is shown over here. It could be positive, could be negative, right? Positive in this case meaning there's an intruder, negative meaning there's not an intruder, or there's not an intruder I care about. And then the prediction is what comes out of your system, right? An alarm says, I think there's an attacker. And no alarm says, I don't think there's an attacker. And so for a true positive, you've got an alarm and in fact an attacker is present. For a true negative, the alarm is quiet and there is no attacker present. But you can also have the other cases, a false negative, right? There's no alarm, but there is in fact someone who's an attacker present. And a false positive, the alarm's going off, it's blaring at you, it's deafening, but there's not really a problem. Okay, just something that you should know. So the next tactic is delay. If we can't deter you, and maybe we detected you, but it would take us a while to respond, so we want to delay you while we organize a response. Delay is often done with locks or fences or those kinds of things. Okay? Locks are a delay tactic, right? They're not going to perfectly deny you access. A locked door is still a door. A locked gate is still a gate. A fence could be climbable, right? Or you could tunnel under it. There's a million different ways to get around these things. Are there really a lot of ways to get around this? I mean, look at that lock. That lock in that picture looks pretty tough. What can I do about it? How would I get through that gate? So I want you to stop for a minute here and think about, how would you get through this gate? What could you do to get through this? So give it some thought, come up with some ideas, and when you're ready, continue. All right. Let's see some ideas. Well, one thing is you might shim the lock. What is shimming? Well, the lock has these little locking bolts that go into detents on the shackle. That's that curved thing that hold the shackle in place. But if I can slip something down between the body of the lock and the shackle, I can possibly push those out of the way and then release the lock. If you want to know more, there's a link to a video in the slide notes that will let you see how you can shim a lock. You might cut or break the shackle. I mean, it looks pretty tough, right? But trust me, you get some leverage on that, you can snap that thing. And in fact, there's videos of how you might break the shackle where it's weakest to break the lock open. Or you can just cut it. Just come at it with a big old pair of bolt cutters and just cut through the shackle. You could pick the lock. Padlocks are notoriously easy to pick. It's a great way to get started with lock picking. Lock picking is fun. I recommend you play with lock picking for fun. Don't go doing anything malicious. But you can pick that lock. That's another way to get through it. There we go. Or, look at that bolt sitting there. How is the whole thing held on? It's held on with that bolt. So if I take that bolt off, can I just remove the whole thing? Sure I can. Yeah, take the bolt off, unscrew the bolt, and you're done. I don't have to pick anything or break anything. I just take the bolt off. I could cut the fence. If I cut the fence, I can just walk through the fence. That will work. That takes some time, though. There's a video of showing you how to cut fences in case you're curious about that. I could climb the fence or jump over the fence. Some good videos there you should watch. Maybe the fence is like short and I can just hop over it. I can do that. Maybe it's tall, it's hard to climb. So then maybe I do one of the other things. I'm building up a lot of options here. I could lever up the fork. Really? Could I? Could I do that? Sure. So if you look, 7 happens to be pointing to a little nub there on the side. That nub is part of a pin. The fork is the piece of metal going off to the right. The fork that goes over that little tube there. And as I try to push it up, I'm pushing against a bunch of stuff. I'm prevented from pushing it too far because of the lock. But if I push hard enough, I might break the pin that's pointed to at 7 and be able to raise the lock. Or maybe I have enough play in the system that I can just raise the fork far enough that I can open the gate even though the lock's still on it and nothing breaks. Believe it or not, I've seen many cases where that's the case. Or I can disconnect the gate hinges. Really? Yes. I've got a link to a video there where firemen will show you how to use a Halligan bar that we've talked about before to just remove the hinges, take the gate off, ignore the lock, just take the thing off the hinges and just walk in. Surely that's all of it. There are probably a dozen more different ways to get through it. So let's talk about response. So response is just what it says. It's a physical response to usually a predetermined location. And this is going to be based on information provided by your alarms, your intrusion detection, etc. And the response is equipped with the force necessary to stop the advancement of the adversary. The adversary is advancing, right? They've gotten through a gate. They may have gotten through a door. They may have gotten through another door. But you've got to get there and prevent them from advancing any further. Okay? So you want to stop the advancement of the adversary. So when an alarm occurs, you have to do two things. You have to diagnose the alarm, right? The alarm's going off. What is that noise? What is it telling me? Oh, it's telling me that someone has opened a door that shouldn't be open, or it's telling me that there's motion in a hall that should be motionless and empty. And then you need to respond to the alarm in a way that stops the advancement of the adversary. Typically, you might lock down an area by disabling a whole bunch of stuff around it so they can't get through subsequent doors, or it's difficult for them to. But more likely what you're going to do is you're going to send often armed guards to go and grab them, just like they've grabbed this poor fella here. He looks happy about it though, so it's probably fine. And then finally, neutralize. You want to render the enemy personnel incapable of interfering with your operations. How would you do that? Well, the picture there of this glass door is actually a device. That device is commonly called a man trap. But I'm sure you can trap women in there too. The idea is that once they go through one of those doors, all the doors lock and they can't get out. And you just trap them there until you can get police or armed guards or whoever there to take custody of them. They're stuck. They're just stuck inside there. Usually they're constructed out of bulletproof glass, so they can't shoot their way out. They're just stuck. They're just there until you can go get them at your leisure. So one thing you might notice about all this is we talked about this guard at the very beginning. He was there. Yeah, I put him up for the deter picture. He looks mean. I don't want to cross him. He looks like pretty tough. But he could actually do everything, right? He can deter you. He's got eyeballs looking around so he can detect you. He can delay you, right? Because if you're trying to get into that thing behind him, he's going to be there, and you got to get around him. He might wrestle with you. That's going to slow you down. He might shoot you. That's going to slow you down. Right? There's a number of ways that he can slow you down. He's right there, so if you wanted a response, he's already there to respond. And he could potentially neutralize you too, right? He looks pretty tough. So, in fact, yes, the guard can do all these things. But that causes you to have a single point of failure, right? What if the guard is neutralized? What if the first thing you do when you go up is you knock the guard out, or you draw the guard away, or the guard falls asleep, which has happened. What if the guard is working with the bad guy? What if the guard is the bad guy? Okay, so you don't want a single point of failure. That's bad. So one of the things about these 5 functions of physical security is that failure is anticipated at each one. They work together when they're independent, when you're not relying on one guard to do them all. They work together to give you defense in depth, or they can work together to give you defense in depth. So when each protective system fails, you have something to fall back on, right? You didn't detect them initially, but something is slowing them down, and that gives you more time to detect them using other methods. So delay, for example, in this case is helping compensate for the loss of detection. So there you go. Create your protections proportionate to the risk that's involved. Don't have a single point of failure. Don't rely on a single protective measure. Whenever possible, you want to cross-validate your protection and use defense in depth. What I mean by all that? Assume a protective measure will be compromised, whatever that might be. So assume, for example, that the alarm system that you put in can be bypassed. All right, what if it is? What's my fallback? Well, maybe I'm having a guard drive by every so often and just look. And they see you, let's say, inside the building, and they're like, well, someone inside the building, the alarm's not going off, but there shouldn't be anyone in that building, so I'm gonna call it in. Okay? So assume protective measures can be compromised. Lots of reasons that can happen. What's your backup when that happens? Assume that they can fail. Yeah, every system fails, right? Every system you put together fails, right? Every piece of software, hardware, personnel is ultimately vulnerable and can fail. And so you need to have a collection of these that work together to secure whatever it is you want to secure. Implications? Well, avoid relying on a single security mechanism whenever possible. For example, increasing use of multi-factor authentication is an example of that. anticipate that protective measures will fail. You can cross-check multiple protective systems. You can have timeouts. You can have re-authentication. Okay? So you're working with some stuff. Maybe somebody gets up from the computer and leaves. Somebody else comes in. That could be a problem. But if the timeouts are set correctly, hopefully the machine is locked and they can't get in. Somebody has broken through your fence and they have disabled the normal detection that would find them, motion detectors or whatever, but you've got cameras, and so you can catch them on the camera. All right. This homework is due the 10th of September, and I want you to think about a physical system and its security. So pick a system. I don't necessarily care what it is. Don't pick anything too hellishly complex, but pick a car or a house, those kinds of things that have sort of familiar security systems associated with them, or whatever you like. And just consider the functions detect, deter, delay, respond, and neutralize for that system. Now, every system isn't going to implement every one of these 5 functions, but it probably will implement a few of them. So for your chosen system, and for each one of these, tell me how it addresses that function, right? How does it detect? How does it deter? How does it delay, etc.? If it doesn't address that function, just say it doesn't address it, but then think, could it? Is there a way that a system could be modified? Right? Maybe it doesn't have the ability to neutralize the adversary. What would that be? How would I modify it so that it could potentially neutralize the adversary? So give this some thought. Really think about what these functions mean, and think about how your system works. You might be surprised when you really get into it. A lot of these things do have a large number of these functions implemented. So give this some thought. And that's it.